the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact. Over to you, Russ, and you can introduce Eric. Sounds good? All right.
Yep.
So welcome to the Spring 2024 Sustainability Seminar Series. So we have put together an excellent slate of speakers this semester. So those of you who are taking the seminar for credit, you guys must have seen the syllabus that I have uploaded in Canvas. If you haven't seen the syllabus yet, then please check the syllabus. The syllabus is pretty much self-explanatory, and we're not going to spend much time here like describing the syllabus. So if you have any questions, please email me. All our speakers have kindly agreed to stay behind after the seminars until 6:20 p.m. to chat with you guys. So use this opportunity to network with some of the best minds in sustainability, and maybe some of them can become your industry mentors in the capstone projects down the road. So after the end of the semester, Khalid will open a breakout session where you can interact with our speaker today, Eric, and then our special guest today, Russell Hyatt. And to attend, you must be a sustainability management student or enrolled for credit in the seminar this semester. So today's seminar is sponsored by Geosyntec Consultants, who are one of the joint sponsors of the Hugo New Sustainability Seminar Series. Russell Hyatt is here from Geosyntec. He will introduce his colleague, Eric Amundsen, who will be our speaker today, the first speaker in Spring 2024 Sustainability Seminar Series. No pressure. We'll talk about
well, I like that it's called Spring. That's good.
Yeah.
It's Spring, right?
That's true. Yeah, it is Spring, yeah. So he'll talk about environmental LCA. Russ?
Thank you. So it is my absolute pleasure to introduce to you my colleague, Eric Amundsen. He's a senior engineer and energy transition consultant at Geosyntec Consultants. Eric, as Dave's mentioned, will be presenting to you and talk about the growing importance of environmental life cycle assessments, and I'm really excited to listen in on it. I'm going to give you a little bit of information about Eric. He has quite the diverse background, and it enables him to give a great perspective and a unique perspective on opportunities and risks associated with the shift to a lower carbon economy. So Eric has studied mechanical engineering at Massachusetts Institute of Technology, where he earned a Bachelor of Science and Master's degree in mechanical engineering, as well as a Master's degree in technology policy. Eric worked as an environmental consultant for a few years after school until he went on to become a patent attorney, practicing patent law for 22 years. But then that pesky old environmental consulting bug bit him again. And in 2021, Eric rejoined the environmental consulting world as part of Geosyntec's energy transition team. And we couldn't be happier to have him on our team. So currently, Eric assists our clients by addressing their energy transition and ESG goals and helping them to identify, manage, and report on opportunities and risks associated with the shift to a lower carbon economy. As part of the energy transition team at Geosyntec, Eric works with clients to prepare environmental life cycle assessments, develop achievable decarbonization goals, tackle the strategic and practical challenges associated with climate-related risk assessments, create internal systems to manage policy and regulatory changes. And that's really just to name a few. He really does it all. So please join me in virtually welcoming my colleague Eric Amundsen to the Sustainability Seminar Series.
Thank you, Russ. Appreciate it. And yeah, and I'm very excited to be on the Geosyntec energy transition team. It's really been my goal to work in the greenhouse gas arena and in decarbonization and life cycle assessment, going all the way back to the technology policy program that I was attending back in the day, which likely has some similarities to the program you're in. I'm very interested to hear more about your program as well. Thanks to all the sponsors here on the initial screen. And then I'll start moving into the presentation, which of course is, as you heard, environmental life cycle assessment. And just a general agenda. I'll be doing an introduction first to LCA, then some examples of real world applications and how people use LCAs, and then we'll have a Q&A session at the end. So first, environmental life cycle assessment. Why might an organization want to perform a life cycle assessment? I think probably all of you have heard the paper versus plastic arguments and articles throughout the years and decades now, and things of that such. And there's been LCA work out of curiosity, people just interested in doing academic research on it, et cetera. But now we've really moved into a time period where LCAs are becoming very important financially, in addition to looking at sustainability from a more sustainability aspect. There's real economic and financial implications now with life cycle assessment. So one or more of these situations on the slide could apply to an organization, or could in the near future. In one example, a customer could request, if you're running a company, a customer could request a product carbon footprint, or an EPD, which is an environmental product declaration, which we'll get to a little later in the presentation. Or in the second bullet point, a construction materials manufacturer may be operating in a state that has a buy clean program, and that program might require an EPD or an LCA for any materials purchased for state projects, whether it's a highway project or some other infrastructure project. A company might have byproducts or waste that they're interested, that normally they just get rid of or send to the landfill. And it might be something that they could receive credits for if they were to generate a biofuel in some way. And they want to look at that and see if perhaps they could get credits for that, or sell the waste to someone else who could generate a biofuel from their byproducts or waste. And another example is, and this is a very hot topic right now in the LCA world, and is hydrogen, clean hydrogen. The Inflation Reduction Act has a tax incentive in there for producing clean hydrogen. And so somebody who's looking at that, an investor, a hydrogen producer, they may want to explore, or not may, but do want to explore whether their hydrogen process could qualify for these, and they're called Section 45V credits of the Inflation Reduction Act. And of course, there's many other reasons to do LCAs. These are just a few examples. Okay, so the overview of the LCA, will be doing what is an LCA, the phases of an LCA, and the areas where the use is growing. So I'll start with what an LCA is. And in short, the shortest sentence I can come up with is, it's a standardized method of performing an environmental impact assessment. And within the phrase life cycle assessment, the term life cycle refers to the entire chain of activities which occur throughout the life of a product, to make and use the product, and including making and using the product, and disposing or recycling of the product. And the term assessment in life cycle assessment refers to the compilation and the evaluation of all these inputs and outputs associated with these activities, as well as the environmental impacts of the inputs and outputs. So that's where the phrase life cycle assessment comes from. Now, the life cycle itself is typically split into 5 separate life cycle stages shown here. And these can vary, or be subdivided further, but this is generally the approach that is taken. In a first stage, you have the raw materials being acquired. This could be growing and harvesting crops. It could be pumping oil out of the ground. It could be mining iron ore, or really any other extraction of materials from nature. I mean, if you take any product or service back to its beginning, there's something being extracted from nature. The raw materials are then transported to facilities for the second life cycle stage, some sort of preliminary materials processing. Examples of this could be crushing crops if you're manufacturing a biofuel. It could be refining oil into various petroleum products, or it could be processing iron ore at a steel mill. And then, of course, there might be secondary processing and all sorts of different, interlinking between the various materials. But eventually, at some point, you get to the product manufacturing stage, and all the various materials are shipped to the product manufacturing site or sites. And this stage includes machining materials, assembling, packaging, and any other manufacturing processes. And then the fourth stage is the use phase. And of course, this is where the main value of the product is extracted. So if it's if you're looking at a transportation fuel, this is the stage where the fuel is combusted. And there are emissions released to the air, and the work is provided to move your car or fly the plane or drive the train. And then, a consumer product, more something along the lines, if you're looking at a consumer product and its life cycle, so say a refrigerator, that would use electricity during its use phase. And this would result, of course, in power plant emissions, and those emissions would be counted as an output of the use stage. In the final stage, it's the end of life stage, and that can involve repurposing, recycling, or disposal. And of course, often disposal is either through landfilling or incineration, or in some cases, a combination if it's something larger that gets broken up into constituent parts. Okay, so that's the life cycle of a product or a service. We'll now turn to the LCA process itself. And there's four phases in a life cycle assessment. And this whole process can be iterative when aspects of a product system are learned or better understood while you're performing the study, or you change your goal or scope of the study as you're moving through. But the first phase on the left-hand side is the goal and scope definition. And this defines the purpose and the system parameters for the study. The life cycle inventory stage is shown in the middle, and that's the accounting phase. That's really that's the numbers crunching, that's the data gathering, and these are where all the input and outputs are quantified. And this is also where a model is typically built to, you typically build a model to represent the flows of materials and energy into and out of the product system. And also flows within the product system as well, not just in and out of the system. Then the impact assessment phase, which is on the right-hand side, this is the phase where you translate that inventory. So you've got all your inputs and outputs, and how much electricity is used, how much fuel is used, all these different materials are used, and then you translate that into impact indicators. And this is a way of looking at the environmental and human health effects. So you might know, okay, we have this amount of emissions of various chemicals, but what does that mean in terms of various indicators? And then at the bottom is the interpretation phase. And this should be ongoing during the whole process, but involves studying results, understanding causes and effects, and then hopefully or potentially providing recommendations for the product system if one of the goals is to understand how you could reduce impacts. But it's looking for hot spots or looking for cause and effect, which a lot of engineers, scientists, and technically oriented people love to do. What are causes and effects? So let's drill down now on the first phase, the goal and scope definition. the goal defines the purpose of the study and the audience for the study. So this can be relatively straightforward in some cases, or there could be multiple purposes. So one example of a goal or purpose of a study, we worked with a client who asked us to perform an LCA for a fuel derived from soybean oil as part of evaluating whether they could, the potential they had for getting carbon credits for biofuels under California's low carbon fuel standard. And so we, performed an LCA on that to give them some indication where they would fall in the California's LCFS. In another example, we performed an LCA for a low carbon jet fuel, or actually many different possible jet fuels, as part of evaluating the potential to qualify for incentives that were in a pending bill in US Congress at the time. Another example is a nitrogen fertilizer product, and I'll get into more detail on that one later. But there was a goal there to support a client in applying for IRS tax credits associated with carbon capture and utilization. And so a lot of these credits and incentives that are coming along involve LCAs and understanding carbon accounting in many cases, but in other cases, other impacts beyond global warming. We also performed an LCA for a material that functions as an alternative to concrete. And the purpose of that LCA was really to identify environmental hotspots to guide research and development efforts as the client was developing their system of and their whole process, as opposed to looking at certain incentives or really trying to compare it to some other alternative. They were really trying to optimize or improve their process. And in the final example here, we did an LCA for grid scale batteries as part of a governmental loan application, where the government application required showing reduction in air pollutants and greenhouse gases relative to a business as usual case. So we had to model the business as usual case and then also how this new grid scale battery would operate and compare those two. Okay, so turning now to the scope definition portion of the first phase. This is where the product system is defined. So, and the functional unit is defined, and the system boundary is delineated, and also a decision is made in terms of which environmental impacts are being assessed. Now, the product system is a group of subsystems or unit processes that provide some ultimate function. And I'll note here that, this function could be, the product system could be a service system rather than a physical product system. And then you define a functional unit. So in some cases, the functional unit is a measure that's used to link all of the inputs and outputs to a specific quantity or specification of functionality. Because if you are planning to use this as a comparison in some way, you want to all be comparing to the same thing, but you also want to be tying everything to a specific output so that the modeling makes sense from a mathematical standpoint. So for example, for a product system where the production of gasoline is the ultimate sole product that is being produced, that you're trying to get some LCA numbers for, the functional unit could be defined as 1 gallon of gasoline with a certain octane rating, or it could be defined as enough gasoline with an energy content of 1 million BTUs. But something that really gets at the function of gasoline, which is to provide energy. And so you want to look at energy content most likely in some way, but you could put that in terms of kilograms of gasoline or gallons of gasoline, because it's a fairly standardized product. In other studies where the functional unit's not a fuel, but say a product like a consumer product such as a refrigerator, the functional unit could be a refrigerator that provides a defined amount of cooling at a certain efficiency. Just to say, oh, it's one refrigerator. Obviously, there's a variety of refrigerators, so a functional unit of one refrigerator isn't going to be comparing apples to apples. And then to say, oh, well, to provide this certain amount of cooling, that may not be enough either, because, okay, this refrigerator provides cooling, but it uses twice as much electricity to do so as this one. So we want to make sure we're normalizing things best we can. And then for the system boundary, I'd gone over those 5 phases or 5 stages of a product life cycle. The system boundary defines which life cycle stages you're including in your study or in your inventory. So you might just look at the impacts up through the manufacturing stage, but not include the use stage or the end of life stage. And so this would be a system boundary in the top example. That's referred to as a cradle to gate, because it tracks the inputs and outputs and impacts related to from the raw material acquisition stage, that's the cradle, all the way up through the exit gate of the manufacturing facility where the product is ready to ship. So that's the gate. So that's the cradle to gate study. An LCA with a full life cycle is typically referred to as a cradle to grave LCA, and that accounts for the impacts all the way through to the ultimate disposition of the product, such as recycling or disposal, and that's shown in the bottom example here. As I mentioned, the scope definition also includes listing the impact categories to be evaluated, which could be one or it could be many. A few examples are global warming potential, acidification potential, and ozone depletion potential. Those are some examples. All right, so now we'll move on to the life cycle inventory phase. So once you've defined your scope and your goal, which again might be revised as you move along, you move into the inventory stage. And here you look at the inputs and outputs for each stage that you're setting, and you compile them using various types of available data. Each stage could have an energy or materials inputs, and it could have emissions, air emissions. There could be, discharges to water, discharges to land, although not so often discharges to land. But you have wastes and emissions as outputs. And this could occur at various intermediate steps. Other times there might not be emissions or wastes at different stages. And then any one of these intermediate stages might have useful byproducts as output, something that is sold off or given away to somebody. And when you set up a model to track all this, you typically track the inventories at each stage. You set up each stage and you do an inputs and outputs list. And you can use a spreadsheet model, but there's a lot of different commercial software out there as well, where they've set them up so that you can help track and develop these inventories. The data itself, this part can be really difficult and take some strategy and really can take a lot of work. But the data can come from various types of sources, and you're looking for 2 types of data. You're looking for the data in terms of inputs and outputs, and then you're also looking for emission factors. So you might figure out, oh, we're buying 100 gallons of oil a year for this production facility. Okay, how did you get that 100 gallons? That's one data point you need. But then you also need to know how many emissions of carbon dioxide was there to get this oil to our plant. Like, that oil had to be pumped out of the ground, it had to be refined, it had to be transported. You don't want to go back and do that study in addition to whatever you're studying. So you look to either your supplier, do they have information on that, that data, or you look to there's commercial databases that are sold, and there's publicly available databases that have averages for some of the more typical materials you might be sourcing. So you're looking for different types of data. So you can get data from databases, you can get it from other LCA studies. You can, like I mentioned, you can get it from commercial databases, but there's any number of places. And then data that you actually measure in terms of, okay, what are our on-site emissions, or what are our on-site fuel usage? And sometimes it can be a direct measurement. Other times it's an estimate. Like, oh, well, we sample this stack once a month, and we sense this much nitrous oxide in it, and we know that we put out this much gas overall from that stack, so we're going to extrapolate and get numbers. So there's a lot of different ways that some of this data has to be acquired. For one LCA that we recently conducted, the data for the on-site feedstock and fuel use and the masses of the output products came from some actual measurements at a pilot plant. The air emissions and the air emissions data came from computer models rather than in actual measurements. And then the upstream emissions, looking at, okay, we purchased these materials and these fuels, what are the emissions associated with sourcing those raw materials? Those, the emissions for that were estimated using a publicly available LCA model from Argonne National Laboratory, which I'll briefly discuss. And also some data from a commercial data set provider where the Argonne model didn't have particular data. So as you can see, the data can come from a variety of sources when you're conducting the inventory. All right, next I'll discuss the impact assessment phase. And this is the phase where the inventory of the inputs and outputs is translated into impact indicators. So here, say for example, we're doing an LCA with these 5, and as I noted, you may only have one impact indicator. We've done a number of LCAs where people just want greenhouse gas emissions and global warming potential. But in other cases, a larger number of categories may need to be considered. And so here's 5 examples. And for any given category, and we'll use global warming as potential as an example, different compounds have different levels of effects on these categories. So typically what we'll do is bring it all back to a single indicator so that the various compounds are scaled to that indicator, because putting out data, well, there's this much carbon dioxide, there's this much nitrous oxide, there's this much methane, comparing that to another, some other LCA that has those same but different numbers, it's a lot harder to compare. So for example, when carbon dioxide is the greenhouse gas that's most typically discussed with climate change. So with these other greenhouse gases, you bring it back, and these other to carbon dioxide, and some are more potent than others, but they have different levels of persistence in the atmosphere. So that that can also make it a little more difficult. But what we typically do is a carbon dioxide equivalent. So you look at, all right, there's methane, there's nitrous oxide, there's what's the big one? It's SF6. It's like hexafluorine or something, and there's lots of different compounds that are considered greenhouse gases, and we bring them all back to carbon dioxide equivalents. And so the amount of methane that's converted to a similar amount of carbon dioxide that would cause the same amount of global warming as that methane. And I'll show an example of that on the next slide. And there's other indicators shown here. So for example, for ozone depletion compounds, which are not CFC11, you would scale them to an equivalent amount of CFC11 that would have the same depletion effects. All right, so for the math section of the presentation, I'll go through one example of calculating the amount of CO2 equivalents or carbon dioxide equivalents. So let's say you've completed your inventory for the entire process for greenhouse gas emissions, and you're studying these, and you're including just these 3 emissions, these 3 gases, and this is what you get for every functional unit. So let's just say there's one widget that you manufacture and ship out the door. There's 100 kilograms of carbon dioxide, 1 kilogram of methane, and 0.4 kilograms of nitrous oxide that are released. So now we're going to do the assessment and tie these all back to CO2e, carbon dioxide equivalent. And to do this, we're going to use the 100-year global warming potential indicator. As I mentioned, all these gases have different levels of persistence in the atmosphere. So you have to somewhat arbitrarily define a time period that you're looking at to normalize the global warming potential, because there could be a gas that is really has a lot of global warming potential but lasts for 10 minutes. So how much is that really going to affect global warming? And then you might have something else that has a minor effect on global warming, forcing, radiation forcing to it, but it lasts for 100 years before it goes away. So that's going to have a different effect. So what time period you look at is going to change things. And so often global warming potential of 100 years, a 100-year time period is what's used. 20 years is another common one, but regulators often use the 100-year global warming potential. So since we're bringing this all back to CO2e, we define 1 kilogram of CO2e or 1 kilogram of CO2 as 1 kilogram of CO2e. So here we have 100 kilograms of CO2, that's 100 kilograms of CO2e. All right, then with methane, it gets a little more interesting. So you have 1 kilogram of methane, but that is the equivalent of 29.8 kilograms of CO2 being in the atmosphere. And this gets revised as more and more studies are done. This number changes a little bit every couple of years in terms of what people are using. I think the prior number was 27 point something, but then it got upped a little bit for methane. And so here, 1 kilogram would equal 29.8 kilograms of CO2e. And then when you do the same thing with nitrous oxide, get a bigger number because it's a more potent greenhouse gas. And so its scaling factor is 273 kilograms of CO2e. So here, even just less than half a kilogram of nitrous oxide ups your global warming potential number by more than the 100 kilograms of carbon dioxide itself did. And then if these are your three gases, you sum them all together and you get approximately 239 kilograms of CO2e. And that would be the number that's often shared in the LCA. Like here's the global warming potential indicator results of our study. Per widget, there's this much emissions in our value stream. And you could do the exact same thing with the other indicators. Figure out for each type of emission or output that has an effect, bring it back to that consistent impact indicator. All right, so where are we seeing an increase in the use of LCAs? Our clients are often receiving requests from their customers for LCA information about our clients' products. And in many cases, they're requesting information about carbon intensity. So that's the CO2e from the prior slide. And those customers of our clients are requesting the information because those customers are doing their own LCA study. And one of their inputs is whatever our client is selling to them. And so rather than that customer doing an entire LCA study for that one input, they're asking, hey, what do you have for a carbon intensity? So we can just plug it into our calculations. Similarly, with the second bullet point, it can assist with a client's customers' corporate greenhouse gas inventory. If they're looking at their greenhouse gas inventory, not just for their own facility, but all of their upstream, purchases and activities, again, they're going to ask their suppliers for, okay, what's the carbon intensity of each widget that we buy from you? Let's move to the third bullet point. For biofuels, say investors want to explore the long-term viability of certain biofuels from a carbon standpoint or other impacts, environmental impacts, when they're looking at fuel standards or fuel incentives or things of that nature, and they want an LCA to help with that evaluation. California, Oregon, and the state of Washington each have a low carbon fuel standard, and an LCA is required as part of calculating the carbon intensity of fuel sold in those states to receive those credits. The next bullet here is the Buy Clean programs, which I mentioned earlier, and these are coming into force in various states. And some of these programs require that environmental product declarations be developed for construction materials purchased by the state government. And there's also a federal Buy Clean program as well. And these environmental product declarations are based on LCAs. So here again is where LCAs are starting to be used more and more. And then at the state level, I'll just mention California has incentives for geologic carbon sequestration. But when you're sequestering carbon dioxide, you're using energy to pump the CO2 underground. And the California program requires that you perform an accounting for those emissions. associated with that energy to sequester carbon dioxide, because you are having some other emissions, and they include those within the incentive calculations. And finally, there's various tax incentives for certain low carbon related activities. I mentioned Section 45V of the Inflation Reduction Act, which is for clean hydrogen production. There's there's carbon capture and utilization and sequestration. So there's a number of different areas where there's now real tax incentives, and understanding these numbers becomes important. All right, so now I'm going to move into more detail on very specific, specific applications for LCAs and go through some examples. So this 45V tax credit, it was in the Inflation Reduction Act, which was signed in the summer of 2022, and it provided quite a large potential tax incentive for people producing clean hydrogen. So it offers up to $3 per kilogram of hydrogen that's produced based on the product's cradle to gate life cycle greenhouse gas emissions rate. And as shown in the graph, you can see the maximum value is $3 per kilogram. And that's for hydrogen that has a life cycle emission rate of less than 0.45 kilograms of CO2e, carbon dioxide equivalent, per kilogram of hydrogen. And then you see there's other thresholds. So this is fairly unique in terms of incentive programs, where there's a stepwise function to it, where if you can get lower and lower, you can get a higher and higher tax credit. And the IRA, the law said this cradle to gate emissions factor, or emissions answer, has to be determined under the most recent GREET model, or a successor model. So what is the GREET model? The GREET model, it stands for the Greenhouse Gases, Regulated Emissions, and Energy Use in Technologies model. And this was initially developed by Argonne National Laboratory in 1995, and it's had annual updates and expansions. It's an Excel-based tool, though I guess they're looking at maybe trying to change that, because as any of you have slowly built onto an Excel file more and more, it's not exactly super user friendly at this point, because they've always had to kind of not change what they've done before very much. The most recent version of the GREET model is GREET 2023, and that was released toward the end of December in 2023. So now I'll walk through a quick example for blue hydrogen with under 45V. Blue hydrogen is hydrogen that's produced from steam methane reforming or other fossil gas reforming of natural gas, but with carbon capture and storage, or CCS for short. So, and I'll note that often people refer to conventional hydrogen from steam methane reforming as gray hydrogen when there's not carbon capture. They'll call that gray hydrogen. And then if there is carbon capture, they'll call it blue hydrogen. And if it's electrolysis using renewable energy to make the electricity, that's often called green hydrogen. So here I'm presenting the well-to-gate greenhouse gas emissions. This is based on the GREET model using a lot of their default assumptions. And this is kilograms of carbon dioxide per kilogram of hydrogen produced for both gray and blue hydrogen. And, I won't step through all what's going on here, but it's just looking at, okay, well, there's some CO2 capture, so that's much lower initial emissions, but then there's more electricity and no steam export. So, but when you compare them, you can see the blue hydrogen is significantly lower. It's 3.4 as compared to gray hydrogen at 9.4. And if we translate that into 45V, that 3.4 gets you over here where the maximum the maximum would be up to 60 cents per kilogram produced. Okay, it was December 22nd to be exact. The IRS released their proposed calculator tool for these 45V calculations. And I'll note that the example I just showed was not based on this proposed calculator. And that proposed calculator draws from GREET, but it's a much more simplified version where you can only plug in certain numbers. And then ways that you could affect that greenhouse gas emissions rate, if you're trying to bring your number lower, you could look at, of course, different hydrogen production technologies. Instead of steam methane reforming, there's other options. And you can try to improve their energy efficiency of that technology. You could also evaluate different feedstock choices. Are you getting your natural gas from fossil gas? Or are you getting it from renewable natural gas? Are there are other ways you're getting methane? Whether you're getting your electricity from the local grid, or if you're able to source it from renewables, and then also finding opportunities to limit leakage or improve efficiency throughout the whole process. And then, as I mentioned earlier, there's carbon sequestration, which is a new area, but it's gaining traction again because there's incentives for carbon sequestration. All right, so now shifting over, I'm going to walk through an LCA project example. And this was for a process where the process was designed initially to convert waste materials, just to get rid of the waste materials that might be a contaminant in soil, but can be used to actually create hydrogen. And this LCA was completed prior to the Inflation Reduction Act, but we can look at it through that lens. And a little bit of background on the technology. It's a smoldering combustion reaction that takes feedstocks and it, now not just contaminated things, but you can take woody biomass, agricultural residues, recycled rubber and car tires, municipal solid waste or recycled plastics, and other inputs like steam, air, and a catalyst. And these all feed into the reactor. And the vapors that come off are fed into a pressure swing absorption unit, and you can get a hydrogen product as well as a natural gas co-product, so methane co-product. And then there's various emissions, carbon monoxide, carbon dioxide, and water. And there's a generation of surplus heat with this. And this process is referred to as an H2 star technology. And I'll show you, these were the base case life cycle assessment results, and they're cradle to grave for the hydrogen produced through the H2 star process. And the bar graph shows the cradle to grave greenhouse gas emissions in terms of kilograms of CO2e per kilogram of hydrogen. And it's in 3 different scenarios. And if you look at them, you'll see, well, these numbers are pretty high compared to what we were looking at before. We were talking about numbers that were 3 or 9, and now these are 20, 30, and 50. And these experimental results, these were based on bench scale experiments performed for this technology, and then upscaled values, theoretically would show the upper and lower bounds. But part of this LCA, we also performed a hotspot analysis to figure out, okay, are there any hotspots here that contribute disproportionately to the impacts of the overall LCA results? And the high energy carbon feedstock, HEC, was identified as a hotspot in this case. And that's because it's a coal-derived product. And in talking with the researchers developing the H2 star technology, it was figured out that maybe this high energy carbon feedstock isn't needed. And so we did a scenario analysis where none of that feedstock is used, and instead it's replaced with additional waste organic carbon. And then those numbers, those results, you can see without that higher energy carbon feedstock, the total greenhouse gas emissions are significantly reduced for all 3 cases of the high efficiency or low efficiency values. And so then we did also a benchmarking results where we compared the cradle to gate LCA results for H2 star against other various production methods for hydrogen, including the conventional steam methane reforming, which we were talking about before, the SMR, coal gasification, and various other ones. You can see it comes in quite low when you're not using that high energy carbon. So we can see that, these are significantly lower compared to these other hydrogen products. Even, it's on the order of this electrolysis with 100% renewable energy. And tying us back to the 45V credits, this is looks like a very viable candidate for this kind of tax credit because it's nice and low on the greenhouse gas emissions side. So here's the up to $4 amount shown there in green. Okay, now I'm going to discuss a second example, and this ties in to environmental product declarations. That's the next step with LCAs. So in EPD, environmental product declaration, EPD it's a standardized report that's based on an LCA, and it transparently describes the inputs, the manufacturing processes, and the environmental impacts of the product across its entire life cycle. And often they're cradle to grave. They can also be cradle to gate. And verified EPDs are sometimes referred to as ISO 1425 type 3 claims or labels. So International Standards Organization 1425 is a type 3 environmental claim. And there's many different reasons to develop these. They can improve business to business communication, as well as business to consumer communication, and they can help with verifying a product compliance with certain regulations or targets, and they can also inform product research and development. And what's helpful is, rather than just say business to business, one business says, hey, I want to know your carbon intensity and your ozone depletion potential. One business may say, okay, great, we did a life cycle assessment, here you go. Well, the person receiving it is going to be like, well, this report is set up differently than I've ever seen. What am I looking for? How do I know what is what? If you do go through an EPD program, which I'll discuss, things are more standardized in terms of how it's presented, what's being presented, and there's somebody verifying it, looking at it, and trying to find if there's been a mistake or something in there. And so it's helpful just in terms of standardization and a little more trust in terms of what's being communicated. In addition, these Buy Clean initiatives, many of them they're driving EPD development right now because they require that there be an EPD. They don't necessarily require certain thresholds of environmental impacts, like, oh, you have to make sure your carbon intensity is below 123 or something like that. But it's just you have to have performed an EPD, so you've measured and estimated the number. And so. And but some of them do have limits, and probably will have limits on what they can be going forward, or factors into the calculation of which contractor or material you buy. So California and Colorado already have these policies in place, and many other states have committed to developing them under the 2023 Federal State Buy Clean Partnership. All right, so now I'm going to walk through the steps for developing an environmental product declaration. Step one is to select an EPD program operator. There's different operators out there that have set up these systems or set up EPD programs, and so we call them program operators. And a program operator registers and publishes the EPDs, and they often, or they do, have specific guidance for how to develop those EPDs. Step two is to select, if it exists for your product, a product category rule. So that'll be something very specific. Okay, I'm manufacturing steel or I'm manufacturing concrete. What specifically do I have to report on and include in my EPD? The PCR will lay that out for you. And then if there's not one for your product, you might have to work with the program operator to develop one, which can involve, it can be a long process, but it's, program operators are interested in having additional and new product category rules. Step three is the meat of it, where you conduct an LCA according to that PCR. And you do all your data collection. What are the inputs and outputs? You feed it all in, run your calculations, get all the different impact indicators, and then put it into step four, which is you develop the EPD by translating all those results from the LPA into the EPD report format that's laid out the rules in the product category rule. And you submit that. So step 6 is register and publish. You submit that to the program operator, and they either internally review it or send it out to a third-party contractor and review it, and try to make sure the T's are crossed and the I's are dotted, and then they publish the EPD. And they're typically valid for 5 years once they get published, and so you can go around and hand them to other businesses and say, here's our EPD for this XYZ product. And one example here, we're getting tight on time, so I'll move through this one pretty quickly, but this was a client wanted to do an EPD for nitrogen fertilizer. So part of it was they wanted to be able to call their fertilizer a blue ammonia certification. And we looked around at program operators and we found there was only one published product category rule for mineral and chemical fertilizers when we started this. And so we selected that program operator because they had a rule, a product category rule that we could use. And so that's how we selected that. It was this EPD North America here in the end that had that we could use. And these are some other examples of program operators. Okay, so then we performed the LCA. We scoped out, did our scoping exercise. We used a functional unit of 1,000 kilograms of the product plus its packaging. That's often the product category rules include the packaging as part of it. And we did a cradle to grave, and we've got the core processes with transport of materials to the fertilizer production plant, fertilizer production processes, generation of co-products, all of this factored into it. And we can now move on to the inventory analysis stage, and we looked at the total impact, but then we have to allocate it. So this is where LCAs can get more complicated when there's co-products, and you have to address or treat those co-products in a certain way, because you're not just producing hydrogen or you're not just producing fertilizer. So you want some credit for these other things that you're producing, because if you take all your emissions and say, oh, all our emissions should be assigned to the fertilizer we're producing. Well, what if you're also producing steam and methane and iPhones somehow? All these different things are coming out. You should get credit for that in some way. And so one way, and I won't go into all details here, but you can do a mass allocation in certain things where you look, okay, we're doing this much mass of fertilizer, but we're also doing this much mass of methane. And we're just going to say, well, if 40% of the mass is methane, we're going to assign 40% of the impacts to methane and 60% to the fertilizer. But the product category rules will usually lay out what the approach should be. So here's the results. I'm only showing the global warming potential results here. And if you look at this, you'll see, okay, the upstream, core, and downstream. Upstream is sourcing of all the inputs and things like that to the facility. Core is the actual fertilizer facility, and then downstream is the use and ultimate disposition of the fertilizer. And what's interesting here is when you look at the breakdown, you see that the downstream is very large, and this largely comes from the impacts associated with applying fertilizer to soil. It's a nitrogen-based fertilizer, and that nitrogen enters the nitrogen cycle and can result in nitrogen compound emissions, some of which is nitrous oxide, which has that very high global warming potential. And then the final step is transferring that LCA into an EPD format for submittal to the program operator. All right, so in summary, closing summary, life cycle assessment evaluates the potential environmental impacts of a product system over its entire life cycle, or whatever selected portion of that life cycle is part of the study. We're seeing a large increase in requests for LCA studies, especially relating to state and federal low carbon fuel standards, the Inflation Reduction Act incentives, sustainable aviation fuels, and interest in EPDs for these buy clean programs, as well as product certifications and marketing and stakeholder interests. You know, when it comes to sustainability reports, ESG reports, people are often looking to quantify some of the improvements they've made. They're also, as they have been in the past, but are still being used, LCAs for research and development, for improving optimization and efficiency of various technologies. So with that, I'd like to thank you for your time and attention, and I'm interested to hear your questions. Well, thank you.